there would be no warning. No telescope would find an approaching front. No detector would register a signal early enough to matter. In the standard picture of false vacuum decay, the event begins as a microscopic quantum transition somewhere in space. A bubble forms. Inside it, the vacuum has had settled into a lower energy state. The boundary then expands at nearly the speed of light, replacing the old vacuum as it moves. Any light announcing its arrival would have no meaningful head start. EA's Science Direct. That is the image most people remember. It is also the part most likely to be misunderstood. Vacuum decay is not a forecast. It is not a known event waiting on a calendar, and current calculations do not make it a practical danger. Under the standard model alone, analyses place the lifetime of our present vacuum vastly beyond the current age of the universe. The threat is not its probability. The threat is what the possibility reveals. The laws that make matter possible may depend a state of empty space that is stable only in the temporary sense. In ordinary language, a vacuum means nothing is there. Physics does not permit that simplicity. Remove every particle, every atom, every photon, and the quantum fields remain. These fields are not optional decorations placed inside space. They are part of the structure from which particles and forces emerge. What we call empty space is the lowest energy condition those fields occupy, or at least the lowest condition they have reached. The distinction matters. A ball resting at the bottom of a valley is stable. A ball resting in a shallow basin on a mountainside can also remain still, perhaps for an extremely long time. Yet the second ball is not at the lowest possible point. A barrier separates it from a deeper valley. Classical motion cannot carry it through. Quantum mechanics leaves another route. A metastable vacuum is the field theory version of that shallow basin. It can behave as stable across every experiment, every civilization, and every recorded age, while still failing to be the true ground state. The escape would not require it to climb over the barrier. Quantum tunneling allows a transition through it, with a probability that can be extraordinarily small, without becoming exactly zero. Peeps, Journals 3. The field at the center of the modern argument is the Higgs field. Its familiar role is to help determine the masses of elementary particles. But once the Higgs boson was measured, its properties became evidence about the shape of the Higgs field's energy landscape. The top quark matters as well. So does the strength of the strong nuclear interaction. Small changes in these measured inputs alter how the Higgs self-coupling behaves when calculations are extended to energies far beyond anything a collider can produce. RCIV. That extrapolation leads to an uncomfortable result. For central values often used in standard model analyses, the Higgs potential may bend downward again at extremely high field values. Our electroweak vacuum would then be metastable, rather than absolutely stable. Yet the conclusion remains sensitive to precision measurements, especially the top quark mass and the strong coupling, and to the assumption that no unknown physics changes the calculation before those scales are reached. ArcSiv. So the evidence does not say the universe will decay. It says the standard model, carried far beyond the territory where it has been directly tested, may permit a deeper state. Those two statements are separated by an enormous distance. Popular accounts often remove that distance because the catastrophe is easier to describe than the uncertainty. Physics has to keep both. Suppose the lower state exists. A successful quantum fluctuation would create a region large enough that collapsing back becomes less favorable than expanding. The energy difference between the two vacua would drive the boundary outward. Within the bubble, the Higgs field would take a different value. Particle masses and interactions could change. The structures that hold nuclei, atoms, chemistry, stars, and living systems together might no longer be available in recognizable form. Saying that everything would be destroyed is almost too familiar. The more precise statement is worse. The categories used to describe destruction could stop applying. there would be no explosion moving through an otherwise unchanged universe. The background rules would change with the front, and still, the calculation says almost nothing about when such an event would occur. A decay rate is not an appointment. It is a probability per unit volume over time, derived from a quantum process so suppressed that the expected lifetime can exceed the age of the universe by an almost incomprehensible margin. Published estimates depend strongly on measured input and theoretical assumptions. Their shared practical message is restraint. If the standard model vacuum is metastable, it appears extraordinarily long-lived. Our sieve, that should make the subject less frightening. Instead, it changes the source of the unease. Human danger usually arrives through a chain of causes we can inspect. A storm develops. An asteroid follows an orbit. A star exhausts fuel. Even black holes announce themselves through gravity and radiation. Vacuum decay offers no comparable object to track. The mechanism is not located inside the universe in the usual sense. It is a possible change in the state the universe is already using everywhere. No warning system can monitor every point in space-time for an event defined by quantum tunneling. No engineering project can reinforce the vacuum. No civilization can move outside the fields that give its matter form. The probability may be negligible, but the vulnerability is complete. That is the contradiction at the center of the investigation. The universe has remained stable long enough to build galaxies, planets, laboratories, and observers capable of measuring the Higgs field. Those same measurements may indicate that stability is not fundamental. It may be endurance. Before asking whether the vacuum can decay, we have to ask a harder question. What evidence could ever justify treating empty space as temporary? The evidence begins with a particle that does not look like a warning. In July of 2012, the ATLAS and CMS experiments at CERN announced the discovery of a new boson, near 125 billion electron volts. Its properties have continued to match those expected of the Higgs boson. That measurement did more than complete a missing section of the standard model. It gave physicists a direct handle on the shape of the Higgs field's potential. A CERN, the word shape, is doing a great deal of work here. No instrument can display the Higgs potential as a landscape. Researchers reconstruct it mathematically from measured physical particle properties and from an equation describing how interactions change with energy. At collider energies, the field sits in the state associated with the world we know. The difficult part is extending the calculation upward, across scales no machine can approach. Couplings are not fixed numbers at every energy. Quantum fluctuations make them run. A force with one effective strength in a low-energy experiment can behave differently when examined at much shorter distances. The Higgs field has a self-interaction described by a quantity called the quartic coupling. If that coupling remains positive as the energy scale rises, the familiar vacuum can remain the deepest available state. If it becomes negative, the potential may bend downward far from the value the Higgs field has today. Several particles influence that running. Higgs and gauge boson effects tend to push in one direction. The top quark, because of its strong interaction with the Higgs field, pushes in the other. The answer depends on a numerical competition among the Higgs mass, the top quark mass, the strong coupling, and higher-order quantum corrections. Current high-precision studies still find that the top mass and strong coupling dominate the uncertainty in deciding between absolute stability and metastability. Marxiv. This creates a peculiar kind of evidence. A collider does not produce a sample of unstable vacuum. It measures ordinary particles, then uses their relationships to infer what the Higgs field might do at energies separated from the experiment by many orders of magnitude. It is like measuring the slope of a road beneath your feet, then using the governing geometry to ask whether the road eventually descends below sea level on the far side of a continent. The calculation can be rigorous, while the extrapolation remains vulnerable to anything missing from the map. With the central values commonly used today, the standard model often lands in the metastable region, not where decay should already have occurred, and not comfortably inside absolute stability. It sits near a boundary. That proximity is often described as a knife edge, but the phrase makes the situation sound cleaner than it is. The boundary is a band shaped by experimental uncertainty, theoretical matching, and the definition of quantities such as the top quark mass. The top quark is especially troublesome. It decays before it can form the bound states that make other quark masses easier to define experimentally. Collider analyses reconstructed mass from showers of particles and compare those events with simulations. The result is extraordinarily precise, but translating it into the exact mass definition required by vacuum stability calculations introduces another theoretical problem. CERN's experimental summaries emphasize that stability depends on the precise Higgs and top masses, while the theoretical meaning of the measured top mass remains difficult to fix at the needed level. CMS 3. Move the top mass slightly, or refine the strong coupling, and the inferred Higgs potential can shift from metastable to stable. One recent analysis concluded that reducing the relevant uncertainties by roughly a factor of 2 or 3 could establish or reject standard model stability at a high statistical threshold. The result would still apply only if the standard model remains correct all the way to the immense scales used in the extrapolation. RSIV. There is no strong reason to assume it must. The standard model does not explain dark matter. It does not provide a quantum theory of gravity. Its simplest form does not account for neutrino masses or the observed imbalance between matter and antimatter. Any new field coupled to the Higgs could alter the running of the potential. It might stabilize the vacuum, deepen the instability, remove the lower minimum, or introduce several new ones. Studies of extensions beyond the standard model find substantial parameter space in which additional fields change the stability picture. ARCSOV metastability is therefore both a prediction and a probe. Carried upward without modification, the known equations point toward a possible lower state. But the scales where that state appears are also where unknown physics has the longest opportunity to intervene. Our vacuum may be stable because of physics we have not found, or metastable only in a model we already know is incomplete. Then there is a different line of evidence. The universe survived its own beginning. During inflation, if inflation occurred, space may have expanded under enormous energy density. Quantum fluctuations would have affected every light field, including the Higgs. After inflation, reheating filled the young universe with an extreme thermal environment. In some standard model scenarios, those conditions could have pushed the Higgs field across the barrier into the lower state. Yet that did not happen within the region that became our observable universe. At first, survival seems to argue for stability. The conclusion does not hold cleanly. The Higgs may have interacted with space-time curvature in a way that protected it. The temperature after inflation may have restored the field toward the electroweak state. Inflation may have occurred at a lower scale. New physics may have modified the potential. Reviews of Higgs metastability in cosmology find that the outcome depends strongly on these unknowns, including the Higgs coupling to gravity and the thermal history after inflation. Ox. 5. Our existence, therefore, supplies a constraint, but not a verdict. Something kept the Higgs field in the state that permits matter like us. We do not know whether that something was a high barrier, a stabilizing interaction, favorable early universe conditions, or the statistical survival of one region among many. The same fact supports several incompatible stories. The early universe was hotter, denser, and more violent than anything that exists now. If those conditions failed to trigger vacuum decay, perhaps nothing in the present universe can. Perhaps. But that answer depends on whether nature has other ways to lower the barrier. A metastable vacuum does not decay because it has been shaken hard enough. That distinction removes one of the most persistent misunderstandings. A particle collision can be violent. A supernova can release more energy in seconds than a civilization could produce across its entire history. A cosmic ray can strike Earth with an energy far beyond anything created in a laboratory. None of this means that concentrated energy simply punches a hole through the vacuum. The barrier is not a wall in ordinary space. It belongs to the configuration of a quantum field. Crossing it requires the Higgs field to move coherently into a different state across a region large enough to survive. Most energetic events produce particles, radiation, heat, and disorder. They do not organize a field into the precise configuration needed to create an expanding bubble. This is why particle colliders are not treated as plausible vacuum decay machines. The collisions produced on Earth occur naturally elsewhere at equal or greater energies. Cosmic rays have been striking planets, stars, and dense astronomical objects for billions of years. If collisions at those energies could easily trigger a fatal transition, the continued existence of old astronomical bodies would be difficult to explain. The argument is stronger than reassurance by analogy. Nature has already performed the experiment on a scale no laboratory can match. Yet the question does not disappear. It becomes narrower. If ordinary collisions are ineffective, could an object with extreme gravity change the probability of tunneling? Black holes are an obvious candidate. Near a black hole, space-time is strongly curved. The usual description of a vacuum transition assumes a background simple enough for the equations to remain manageable. Add a horizon, intense curvature, and a localized concentration of mass, and the calculation changes. Some theoretical studies suggest that sufficiently small black holes could act as seeds for vacuum decay, lowering the action required for a bubble to form. The word "could" matters. This is not an observed process. It is not established that astrophysical black holes are catalyzing transitions, or that any realistic black hole in our universe makes the decay rate significant. The result depends on how gravity, quantum fields, temperature, and the bubble geometry are modeled. It may also depend on physics that becomes important, precisely where the calculation is least secure. Still, the possibility creates a new contradiction. The universe contains black holes across a wide range of masses. Some formed from collapsed stars. Others may exist as remnants of conditions in the early universe, though none of the hypothetical primordial population has been confirmed. If black holes strongly accelerated vacuum decay, then their existence could place limits on how metastable the vacuum is allowed to be. But the inference runs in both directions. The survival of the universe might mean holes are harmless to the vacuum. It might mean the decay rate remains tiny, even with gravitational assistance. It might mean the relevant black holes never existed in sufficient numbers. Or it might mean unknown physics stabilizes the Higgs field before any of these effects matter. Once again, survival supplies evidence without selecting a single explanation. Temperature adds another layer. A black hole is not completely black in quantum theory. It emits Hawking radiation with smaller black holes corresponding to higher temperatures. As a black hole loses mass, its temperature rises. Near the end of evaporation, if the semi-plashual description remains valid, the surrounding conditions become extreme. That sounds like the ideal environment for instability. But high temperature does not automatically favor decay. In some field theories, thermal effects can restore symmetry and push a field toward a safer region of its potential. In others, they can reduce a barrier. The direction depends on the structure of the theory and on which particles interact with the field. Even the most dangerous environment does not come with a simple sign. There is another proposed trigger that appears more familiar: density. Neutron stars compress matter until atomic nuclei no longer remain separate in the usual way. Their interiors reach pressures unavailable anywhere on Earth. If dense matter altered the Higgs field enough, perhaps a neutron star could see the transition. The idea has been investigated in different forms, especially in models beyond the Standard Model. But again, the existence of old neutron stars becomes part of the evidence. Whatever happens in their cores has not produced an expanding vacuum bubble within our observable past. That does not prove the probability is zero. It places severe pressure on models in which the process would be common. The pattern is beginning to repeat. Every candidate trigger seems powerful because it reaches some physical extreme. Can colliders reach high energies? Neutron stars reach high densities. Black holes reach strong curvature. The early universe reached all of these conditions in forms more severe than anything available now. And the vacuum remained. That endurance is one of the strongest reasons the practical risk is considered negligible. A universe that has survived stars, collisions, gravitational collapse, and a hot beginning does not look delicately balanced in the ordinary sense. But ordinary balance may be the wrong concept. A metastable state can survive every disturbance because disturbance is not the mechanism that ends it. The transition may be governed by a probability so low that the entire observable history of the universe is still too short to test it meaningfully. The absence of decay tells us that the rate is small. It cannot tell us that the rate is exactly zero. Consider a radioactive nucleus with a half-life vastly longer than the age of the cosmos. No collision is required. No warning accumulates. Nothing has to weaken it first. At some unpredictable moment, quantum mechanics permits a transition. Vacuum decay extends that logic from one nucleus to the physical state, underlying every nucleus. The analogy is limited. A nucleus decays inside an existing framework of space, time, particles, and conservation laws. A vacuum transition could alter the framework itself. Yet the shared feature is the one that matters here. Stability observed over a long period does not always mean stability guaranteed by principle. It may mean only that the clock is slow. This leaves one remaining refuge. Perhaps the vacuum is metastable in the equations, but some deeper law prevents the fatal transition from ever completing. Perhaps gravity changes the answer. Perhaps quantum mechanics changes near the relevant scales. Perhaps the lower state is mathematically present but physically unreachable. That possibility cannot be tested by asking how hard the universe has already been struck. It requires asking whether our theory of decay is complete enough to trust at all. A decay calculation does not begin by watching a bubble form. It begins by replacing time with a mathematical direction that behaves more like distance. In that altered geometry, physicists search for a special field configuration called a bounce. The bounce is not a photograph of what the universe does. It is the dominant path in a probability calculation, the configuration that contributes most strongly to the chance of tunneling from one state to another. That distinction matters because almost every familiar image of vacuum decay comes afterward. The spherical bubble, the accelerating wall. The interior governed by a lower energy state. Those are physical interpretations reconstructed from a calculation performed in a designed to make the quantum problem manageable. In flat space-time, the basic framework was established before the Higgs boson was known to exist. Add gravity, and the problem changes. The bubble carries energy. Its wall curves space-time. The vacuum energy inside affects the geometry outside. Gravity can alter the size of the critical bubble, the tunneling exponent, and in some cases, whether an appropriate bounce solution exists at all. The process is no longer a field moving across a fixed stage. The stage responds. This is where the apparent precision of the lifetime becomes deceptive. Vacuum decay rates are exponentially sensitive to the action of the bounce. A modest change in that action can produce an enormous change in the predicted lifetime. The equations may return a number with many digits, but those digits do not represent equal confidence in the physics. They often describe the output of a model under standards and assumptions that cannot yet be tested. For the Higgs vacuum, those big to vacuum, those field values may approach scales where gravity can no longer be ignored and where the standard model is unlikely to remain the complete description. Unknown higher dimensional interactions, even if suppressed at accessible energies, can reshape the potential far away from the electroweak state. A correction too small to notice in any collider could become decisive near the region associated with the bounce. The practical conclusion is not that every calculation is useless. The standard model result remains valuable because it reveals how the known theory behaves when extended consistently. It shows which measurements matter, where the instability appears, and how strongly the answer depends on the top quark, the Higgs, and the strong interaction. But it cannot guarantee that nature contains no additional terms before the relevant scale is reached. Gravity introduces its own ambiguity. In the Coleman-de Lucia treatment, spacetime curvature participates directly in the transition. Depending on the vacuum energies and the shape of the barrier, gravitational effects can suppress decay, modify it, or prevent one class of transition while leaving another possible. There is no universal rule that gravity always protects the vacuum or always destabilizes it. The result belongs to the full system, not to a slogan. Journals. Now consider what the lower state actually is. It is often called the true vacuum, as though the phrase identifies a stable destination. In the simplest Higgs extrapolation, the potential may continue downward rather than settling into a well-understood minimum. The endpoint can involve field values where the theory has exceeded its own authority. Calling it true does not mean we know its particle spectrum, its geometry, or whether a conventional spacetime could persist inside it. Some calculations describe the interior as a region with negative vacuum energy. Under gravity, such a region may evolve toward a collapse rather than a quiet replacement universe. But this picture also depends on how the high energy potential is completed. New physics could create a stable minimum. It could lift the dangerous region, and it could change the decay path entirely. The most widely repeated statement says that the constants of nature would change inside the bubble. That is plausible if the Higgs field settles at a different value, because particle masses and interactions depend on the vacuum state. Yet no verified theory tells us exactly what the interior would contain. The confident part is narrower. Ordinary matter is built around the present electroweak vacuum, and a transition far from it would not preserve that arrangement in any simple way. Beyond that, the description becomes conditional. This uncertainty weakens every dramatic claim about the event. We cannot say what the bubble would look like from inside. We cannot specify a final chemistry. We cannot describe a sequence of sensations or even assume that observers remain meaningful across the boundary. The closer the transition approaches the unknown ultraviolet structure of physics, the less justified any detailed narrative becomes. But the uncertainty does not restore the permanence we were looking for. It means that the question of vacuum decay is tied to the boundary between two of our most successful frameworks. Quantum field theory describes particles and forces with extraordinary accuracy. General relativity describes gravity and space-time. A vacuum transition at extreme field values may require both, while the complete quantum theory of gravity remains unknown. The threat, then, is not a well-calculated bomb hidden under reality. It is a place where our equations point toward a possibility and then lose the authority to describe its deepest consequences. That is a more restrained conclusion. It is also harder to dismiss. A false prediction can be corrected by better data. A missing parameter can be measured. Here, the uncertainty may come from the fact that the event asks our theories to operate in a regime where neither has been proven complete. The question is not merely whether the vacuum will decay. It is whether a civilization confined to the present vacuum could ever acquire enough evidence to rule the possibility out. There may be no experiment capable of reaching the necessary field values. There may be no surviving signal from a completed transition. There may be no external viewpoint from which one vacuum can be compared with another. If that is true, then the silence surrounding vacuum decay is not only the absence of warning. It is the absence of a final test. There is one fact every vacuum decay argument must pass before it reaches us. We are here to make it. That sounds trivial. It is not. Our existence filters the evidence before we ever see it. We can only observe a region of the universe in which the vacuum remained compatible with galaxies, chemistry, memory, and observers for at least several billion years. Any region that decayed too early would contain no one capable of recording the failure. This is an example of observer selection. It does not explain why the vacuum survived. It changes what survival can prove. Suppose the decay rate were high enough that most regions vanished before stars formed, but low enough that a small fraction lasted much longer. Observers would necessarily appear in the long-lived fraction. They might examine their surroundings and conclude that the vacuum looked remarkably durable. Their conclusion would be based on real evidence. It would also be biased by the requirement that they exist. The point is not that our universe probably works this way. The point is that survival alone cannot distinguish a fundamentally stable vacuum from a metastable vacuum observed during an unusually long interval. The distinction becomes more serious in cosmological models that produce many causally separated regions. Some versions of inflation allow expansion to continue in parts of space-time while ending in others. Different regions could settle into different vacuum states with different low-energy physics. In that setting, a vacuum compatible with observers may be rare without being surprising to those observers. This is where the subject begins to attract claims that go far beyond the evidence. The landscape of possible vacua appears in several speculative approaches to high-energy physics, especially attempts to connect particle physics with quantum gravity. The number of possible states is sometimes described as enormous, but no experiment has directly mapped such a landscape, counted its viable vacua, or shown that our universe emerged from a process that samples them. These ideas remain theoretical frameworks, not observed geography. Even so, they expose a weakness in the question we started with. We asked whether our vacuum is stable, but stability may not be a universal property of reality. It may be local to one field configuration, one region, or one era. The laws we measure could be the low-energy consequences of where the fields happen to settle, rather than the only laws nature permits. That possibility changes the meaning of physical law. A law usually sounds permanent. The electron has a certain mass. Forces have certain strengths. Atoms have certain stable arrangements. These statements feel like properties of existence itself. In quantum field theory, some of them depend on the vacuum state. Change that state, and what appears to be a law may become a phase. Water can be liquid, solid, or vapor without changing the underlying molecules. A vacuum transition would be more radical. The fields that define particles could occupy a different arrangement, altering which particles exist and how they interact. The analogy helps only up to a point. Ice and steam still obey the same deeper framework. We do not know whether two widely separated vacuum states would preserve enough common structure to be compared so easily. This is the deeper pressure behind false vacuum decay. It suggests that the universe may not be built on laws in the way a machine is built from fixed parts. It may be built on a state, and states can be contingent. The Higgs field makes that contingency measurable in principle. Its mass, its interactions, and its relationship with the top quark give us clues about the shape of the potential. Yet the very calculation that points toward metastability also depends on extending known physics across an enormous range of energy. The result sits between evidence and assumption. That ambiguity has produced two opposite errors. One treats vacuum decay as an approaching catastrophe. There is no scientific basis for that. The estimated lifetime, under the assumptions usually used, is so long that ordinary cosmic hazards dominate any meaningful discussion of risk. Asteroid impacts, stellar evolution, environmental collapse, engineered pathogens, and nuclear war belong to timescales on which decisions matter. Vacuum decay does not. The other error dismisses the subject because the probability is too small to fear. That misses the point as completely as panic does. The scientific value of vacuum decay is not practical threat assessment, it is diagnostic. The question forces our theories to reveal what they assume about empty space, high-energy physics, gravity, and the permanence of the laws they describe. It exposes the difference between a universe that is stable because no laws believe exists, time that survives because the transition is merely suppressed. Those universes can look identical for longer than civilizations, stars, or perhaps black holes endure. No experiment at accessible energy may separate them. Better measurements of the top quark, the Higgs, and the strong interaction could sharpen the standard model calculation. New particles could alter it. A quantum theory of gravity could reorganize the question. But each improvement may replace one uncertainty with another at a higher scale. There is a limit hidden inside every attempt to know the vacuum completely. We are made from excitations of the same fields we are trying to investigate. Our instruments operate within the same state. Our units, clocks, detectors, and bodies all depend on its properties. We cannot step outside the vacuum to test whether it is fundamental. We can only look for internal consistency. So far, that consistency is extraordinary. The vacuum has supported a universe old enough to cool, form structure, ignite stars, build heavy elements, and produce observers. Nothing in the sky suggests an approaching transition. No laboratory result shows that decay can be triggered. No calculation places it with any relevant future. And yet permanence has not been measured. What has been measured is endurance. The difference between those words may be inaccessible to every civilization that ever arises in this vacuum. A species could master fusion, cross interstellar space, manipulate black holes, and survive for geological ages without learning whether the state beneath its existence is absolute or temporary. Its ignorance would not come from a lack of intelligence. It would come from the structure of the question itself. The most silent threat in physics is not a countdown. It is a possibility that cannot announce itself, may never occur, and may remain impossible to eliminate from theory. That makes it unlike every danger we have learned to manage. A dangerous object can be found. A dangerous process can be monitored. A dangerous probability can sometimes be reduced. Vacuum decay offers no such leverage, because it is not a foreign event entering the universe. It would be a change in the physical condition from which every instrument, observer, and warning system is built. Still, the word threat needs discipline. Nothing in current physics justifies treating vacuum decay as an urgent risk. The expected lifetime of the present vacuum, under standard assumptions, extends far beyond the age of the universe. Those assumptions may be incomplete, but incompleteness does not imply danger. New physics could make the vacuum less stable. It could just as easily make it absolutely stable. The evidence does not favor panic. It favors a more difficult conclusion. We have spent centuries searching for the most fundamental layer of nature. Molecules gave way to atoms. Atoms gave way to nuclei and electrons. Nuclei gave way to quarks. Particles themselves became excitations of fields. Each step seemed to move closer to something permanent. Then the vacuum appeared beneath them, and the vacuum may be a state. That is, the reversal hidden inside the entire problem. The emptiness we usually treat as the background may carry more physical consequence than the objects placed within it. A star can disappear while space-time remains. A galaxy can disperse while the fields remain. Even black holes may evaporate while the underlying vacuum persists. But if the vacuum changes, persistence itself loses its meaning. The particles that form matter depend on the fields around them. Their masses, interactions, and stable arrangements are not guaranteed independently of that background. Does not sit above the vacuum like furniture on a floor. It is one of the patterns the floor allows. A civilization could learn every law available inside that pattern and still mistake local consistency for necessity. That mistake would be understandable. Physical laws do not appear temporary in ordinary life. Electrons do not drift between masses. Atomic spectra do not vary from one laboratory to another. The universe is stable enough that precision measurements can be repeated across decades and matched with observations from objects billions of light years away. This uniformity is among the strongest facts science has ever established. Yet uniformity across the observable universe does not prove uniqueness across every possible state of the fields. It tells us that our region shares a common vacuum history. It does not tell us that no other history is allowed. The difference is almost impossible to feel because every human intuition formed inside one phase of reality. We understand instability through visible change. Ice melts, stars collapse, nuclei decay. In each case, the transformation happens within a framework that survives the event. Vacuum decay removes that reassurance. The framework becomes the thing in question. Perhaps a complete theory will eventually close the problem. A deeper symmetry could protect the Higgs potential. Quantum gravity could forbid the dangerous transition. Unknown particles could shift the stability boundary. Better measurements could move the standard model toward absolute stability. That outcome would not make the investigation unnecessary. It would reveal that the apparent instability was a clue to missing physics. The opposite outcome is also possible. Future measurements may strengthen the case for metastability. A more complete theory may contain a lower energy state. Researchers might calculate the decay rate with far greater confidence and still find a lifetime beyond any meaningful horizon. Then the universe would be temporary in principle and effectively permanent in practice. Those descriptions can coexist. A mountain can erode on a timescale too long for any observer to witness. A black hole can evaporate after every star has gone dark. A vacuum can be metastable for so long that no civilization ever sees it fail. From inside, temporary internal may become experimentally indistinguishable. That is where the scientific question becomes an existential one, without leaving science behind. How much permanence can evidence establish? We observe repetition and infer law. We observe survival and infer stability. We extend equations and infer structure beyond the reach of experiment. These are not weaknesses. They are how knowledge advances. But every inference has a boundary, and vacuum decay places that boundary beneath everything else. There may be no final observation that proves the present vacuum cannot end. There may only be tighter limits, deeper theories, and longer survival. The universe has already remained in this state through inflationary expansion, extreme heat, gravitational collapse, stellar death, particle collisions, and more than 13 billion years of cosmic history. That record is not fragile. It is overwhelming evidence of endurance. But endurance is a statement about the past. Permanence is a statement about all possible futures. No finite history can fully establish it. So the absence of warning is not the deepest silence here. The deeper silence is that reality may never provide the evidence required to distinguish an absolute foundation from a state that simply has not changed yet. At the beginning, the threat seemed to be an invisible bubble arriving at nearly the speed of light. By the end, that image is almost secondary. The real disturbance is quieter. Every particle we have measured, every law we have written, and every structure that has survived may depend on the vacuum whose permanence cannot be demonstrated from within it. There would be no warning. But there may also be no final assurance that a warning is impossible.